Welcome. Accuracy and precision, percent error and percent difference is part 2 of a 4-part video series. Part 1 is Sig Figs and measurement uncertainty. Part 3 is standard uncertainty, that is standard deviation and instrument tolerances. Part 4 is combined uncertainty, aka the propagation of error, and you'll find links to these at my website www.chemrat.com. So let's get started. So here's a quick overview of this video. First we'll look at accuracy versus precision, then absolute versus relative error, sometimes called percent error. We'll look at calculation of percent difference, and finally distinguish between systematic and random error. Accuracy versus precision. Well, the definition says that accuracy is the closeness of a measurement to an accepted or true value, whereas precision, sometimes called repeatability, is the agreement between multiple measurements made in the same way. If we use this analogy and say the center of this target represents a true or accepted value, this dot represents a single measurement that is far from the true value, we can say this result is not accurate. And if we've done replicate analysis that are close together, we could say those analyses are precise, but they're still not accurate. In the final case, we have replicate analysis that are close together, and therefore these analyses are precise, and furthermore, they're close to the target, and therefore they are also accurate. So data such as density, melting point, boiling points, etc., that are taken from handbooks that has been determined by repeated, precise experimentation is generally considered to be true or accepted. Now, just to be formal about this, the correct terminology prescribed by official organizations in metrology specify that no true value can be known with absolute certainty. So it is more correct to use the word accepted or reference value. Nevertheless, we'll probably slip into using the word true from time to time. Okay, let's start with accuracy, which is sometimes quantified using percent recovery. So for example, if after adding 10.0 grams of a pure standard to a beaker and running it through an analytical procedure, we might measure the quantity recovered to be 10.4 grams, and we would report 104% recovery. The calculation is percent recovery is measured value over the true or accepted value times 100%, which in our case it would be 10.4 measured, 10.0 known, times 100 to 104% recovery. Now you might be wondering, is that possible to get more than 100% recovery? Well, in fact, it does happen. For example, a sample might be contaminated. A sample that is supposed to be dry may have absorbed moisture and weighed too much at the end. Other impurities might be present, as for example, co-precipitation of extraneous solids in some type of gravimetric analysis. It does happen. Inaccuracy or error is more commonly reported, and we're going to spend the rest of this video discussing that. So error is a statement of the magnitude of the difference between the true and measured value. And you should be familiar with both the terms absolute error and relative error. So absolute error is simply the actual error. It's the difference between a measured value and the true value. In the previous example, the absolute error was plus 0.4 grams. We had 10.4 grams measured minus 10.0 grams actual. And note that error is assigned either a negative or positive value. If the measured value is greater than the true value, as in this case, then of course you assign a positive value to the error. Conversely, if the measured value was less than the true value, you assign a negative value to the error. Note that if no sign is assigned, then we assume it's positive, but if it's negative, you must make sure to put the negative sign in. So here's the formula. Absolute error is simply measured minus true. In our example again, 10.4 minus 10.0 is plus 0.4 grams. Now, absolute error is not nearly as meaningful as relative error. For example, if you were out 0.4 in 1 gram, that would be a lot different than being out 0.4 in 100 or even in 1,000. The relative error is much less in a large quantity. So relative error can be reported in ways such as percentage error, which is parts per hundred, or even parts per thousand if the error is relatively low. And here's the formula for that. Absolute error, in this case 0.4, divided by the true value, in this case 10.0 times 100%. There's the calculation. We would report 4.0%, and we understand that's positive, even though the plus sign isn't shown. Note also that relative error has no units because the units will cancel in the calculation. So this is not grams, it's percent. If you had mils over mils, they'd cancel. It's simply percentage. So let's consider an experiment with a recovery of 49.0 grams on 50 grams of standard that you added. Let's calculate the percent recovery. Now the percent recovery would be the measured value over the true value times 100%. 49.0 over 50.0 times 100% is 98.0% recovery. I'm carrying 3 Sig Figs. The absolute error would simply be the measured value, which is 49.0, minus the true value of 50.0, and in this case we have negative 1.0 grams absolute error. The relative error as percent would be measured minus the true, that's the absolute error from previously, divided by the true times 100, so that's negative 1 gram over the 50 grams times 100 is negative 2%. So despite the larger absolute error in this second case, we're out negative 1 gram on 50 grams, we'd have to say it's more accurate than the previous example where the error was only plus 0.4 grams, but it was only on 10 grams. And that's because the magnitude of the relative error here, negative 2, is less than the error in the previous example where it was plus 4. Here's an example. I'm often asked by students as a teacher, "Sir, do I subtract the measured from the true or the true from the measured?" And the problem is people just forget formulas. So rather than just memorizing, let's try and understand it. So does this make sense that if the measured value was greater than the true value, you'd have too much? That would be a positive error because you measured too much. If on the other hand, the measured value was less than the true value, measured as less than true, you'd have a negative error because you have too little. Try and visualize this. Let's say you had $10 coins in your wallet. Now in Canada, dollar coins are called loonies, so let's say you have 10 loonies in your wallet, and this would be the true value, what you actually have. If you dumped them out, but you counted only 9 by mistake, your measured value is low. Your error is negative 1, and your error is negative 10% because you have too little. So if you had 10 loonies in your wallet, you counted only 9, the error is minus 1. So the percent error must be negative. The error can only be calculated as negative if the true value is subtracted from the measured value. So here's measured minus the true, 9 minus 10, negative 1 over 10, negative 10%. So as a teacher, I am sometimes asked by students whether they should divide by the measured value or the true value. Again, a formula that's been memorized has been forgotten. How do we make sense of this? Well, if you divide by the true value, which you should, you're comparing your error to the true value. And that makes sense. You want to see how far your answer is from the true value. Then you can compare your error with the error from another experiment to see which one's closer to the true value. I mean, really, think about it. Who cares how far the difference is from the wrong value, from the measured value? An example, again, might help you to understand. Let's assume that 10 loonies, $10 coins, are truly present in your wallet, but you counted only 5. You're having a bad day. Let's calculate the percent error both ways and see which way makes sense. So if you do it correctly, 5 minus 10 over the true value, 10, that's negative 5 on 10 and negative 50%. Now doesn't that make sense? You counted only half the number of loonies, so your answer is 50% too low. Well, if you calculate it backwards, if you take 5 minus 10 over the measured value 5, you'd have negative 5 on 5 times 100 is negative 100%. Now does that make sense? No way. If you actually had a negative 100% error, it would mean that you didn't count any loonies at all. So think about it, measured minus the true, compare it to the true. Let's consider percent difference. Occasionally, we don't have a value that's accepted as true or accurate, but we still want to determine the precision or the variation of two measurements. In this case, percent difference is often calculated. Say you had a cube and you wanted to measure its volume. You could do it with a caliper and measure the dimensions, or you could do it by displacing a liquid, say water, in a graduated cylinder. We'll give it some measurement. Let's say the dimensions of this cube as measured by the caliper are 2 by 2 by 2, or a total of 8 cubic centimeters volume. By liquid displacement, let's say we displace 7.91 mils in the graduated cylinder. Let's go ahead and put those numbers in the formula. So the formula shows the difference of the two values, in this case 8 and 7.91. We take the absolute value of the difference divided by the average of the two. The difference is 0.09. The average of 8 and 7.91 is 7.95 times 100, 1.3%. Notice no plus or minus sign. Now what if we reversed the order and took 7.9 minus 8? Well, no problem, because we're taking the absolute value, so that is not reported as negative. It's still 0.09. Likewise, the denominator is going to stay the same regardless of the order in which the terms are added. Again, 1.3%. So note that percent difference is not reported as positive or negative, and because the absolute value of the numerator is taken, the order of subtraction does not matter. Try this problem. A student measures sulfate concentration in the same sample by two different methods. She measures 51 ppm of sulfate by gravimetry and 49 ppm by turbidimetry. Let's say the accepted value is 52 ppm. Calculate the percentage difference that would be between the two measured values, and also calculate the percentage error that would be compared to the true value. So for percent difference, it's simply the difference between the two measured values, 51 and 49, which is 2, divided by the average of the two measured values. The average of 51 and 49 is 50. That ratio times 100 is 4%. For the percent error on the gravimetry, measured minus the true over the true. The measured was 51 by gravimetry, less the true value of 52. The difference is -1, that's the absolute error, divided by their true value times 100 gives you the relative error of -1.9%. The percentage error, or relative error, for turbidimetry is done the same way. The measured minus the true, in this case the measured is 49, minus the true of 52, is an absolute error of -3, divided by the true value of 52 times 100 gives me a relative error of -5.8%. In the final part of this video, we're going to talk about various types of error. It's not merely arbitrary. The way we treat error depends upon the source of the error. Now, there are many terms for human errors, sometimes called mistakes or blunders or miscalculations or illegitimate errors, or even most commonly called gross errors. But these are not experimental errors. In fact, gross errors produce outliers. Outliers are results that are so different from the group that we discard them and don't use them in our calculations. Human errors can be and should be eliminated, but experimental error can never be completely eliminated. It is inherent in the measuring process. So here are the two main types of experimental error. We have systematic error and random error. Now, systematic error, also called determinate error, also called one-sided error, will shift or bias results, always making the final result too high, a positive error, or too low, a negative error, but not both. For example, a thermometer that reads 1 Celsius degree too low will bias all temperature measurements negatively. They will all read 1 Celsius degree too low. Now, systematic errors are reproducible, and they cannot be reduced or eliminated by simple repetition of measurement. However, systematic errors can sometimes be discovered and corrected. For example, a thermometer can be checked against known temperatures, such as the freezing point and the boiling points of water, and a correction can be added or subtracted if it reads too high. Systematic error degrades accuracy, but it has little effect upon precision or repeatability of a measurement. In fact, highly accurate measurements have small determinate error. Now, the second important kind of error is called random error or indeterminate error, also called two-sided error, because it causes measurements to fluctuate above and below a central value. That is, it causes both positive and negative deviations from a mean value. For example, the last digit on a sensitive digital thermometer that is immersed in an ice water bath will be unstable, yo-yoing around a central temperature. For example, plus 0.01, 0.00, minus 0.01, plus 0.01, back and forth. Now, the source of random error is often unknown, hence the name indeterminate, and it is caused by uncontrollable variables. Although it can sometimes be minimized, it can never be completely eliminated. Now, the good news is that random errors will tend to cancel by averaging repeated measurements. The magnitude of random error is quantified using statistics and is reported along with a measured value. For example, we would say the temperature is 0.00 plus or minus 0.01 degrees Celsius. Random error affects precision, not accuracy. Random error is also known as type A error, and systematic error is also known as type B error. Let's look at some sources and examples of systematic determinate error. These errors might arise with the instruments themselves, the methods, or the persons conducting the experiments. In the case of instrument errors, a simple example is a pipette that may deliver less than its specified volume. Perhaps it's dirty, perhaps it's poorly manufactured. We could determine this by weighing the volume delivered by the pipette and calculating the volume. So to correct this, perhaps it's a matter of cleaning the pipette or getting another pipette. A pH meter may be reading 0.5 pH units too low. To check that, we might measure the pH of a solution of known pH value, or we could recalibrate the meter with standards. A balance might be reading 0.1 grams too high on all of its readings. We could check that with a known mass, and we could recalibrate the balance. Method errors. Examples might be impurities in a sample, which can create positive or negative interferences. And to remove this, we might add a reagent to mask it or remove it. Now, reagents themselves can produce interference in analysis, and so typically we would zero an instrument with a mixture of reagents. Alternately, we would subtract a reagent blank. The temperature in the lab will often affect the extent or rate of a chemical reaction. Solution is control the temperature. Another example is that the color intensity of spectrophotometric methods often increases with time. So the solution is to read color intensity at the same time with all standards and samples. How about some examples of personal systematic errors? Well, they are usually judgment errors, not considered mistakes. Color blindness may cause premature or late endpoint detection in titrations. Solution, well, how about using a different color indicator, or perhaps use an instrumental method of endpoint detection. Systematic errors cause the measured mean value x bar to be displaced in one particular direction from the true value, either above or below, but not both. Systematic error can be detected and eliminated. Let's look at some examples of random, indeterminate type A error, those arising from the instruments, the methods, and again from the persons conducting the experiments. As far as instruments are concerned, well, instrument readings do fluctuate due to age, due to electrical noise, due to vibration, etc. A good way to treat that is to take multiple readings and average the results. Alternately, we consider servicing or replacing an instrument whose vibration is objectionably large. Method errors. Now, imprecise transfer of key reagents degrades results. And although it's impossible to transfer reagents exactly, prepare and precisely transfer key reagents with great care and good technique. For example, weigh by difference rather than by addition. Reading analog scales inevitably causes random error, so judgment is required when estimating the final sig fig of any analog scale reading. Now, using instruments with more sensitive scales, such as verniers, will assist in estimating the final sig fig in a reading. Personal errors. Well, even a skilled technologist cannot pipette exactly the same quantity of liquid every time, or fill a volumetric flask exactly to the same mark every time. Some random personal error is inevitable, but good technique hopefully ensures that these errors are negligibly small. Just two more error terms. Dominant error is the term given to one error in a set of measurements that far outweighs all other errors and largely determines the total error in the final result. For example, in a thermochemistry experiment, liquid volumes are measured with accurate volumetric flasks, such as 100 mils plus or minus 0.08 mils. That's only 0.08% error. But temperature changes are measured with a common laboratory thermometer. That, for example, you might measure a 10.0 Celsius degree change plus or minus 0.5. That's a 5% error. So the temperature error of plus or minus 5%, the volume error is only 0.08%. So the error in any value calculated from these measurements will arise almost completely from the temperature readings, and therefore they would be the dominant source of error. Last one, drift. Drift is a gradual but steady increase or steady decrease in an instrument's output signal. Frequently rezeroing an instrument will correct for error due to a drifting signal. Now, drifting is a source of determinate error because it's continually in one direction. Let's summarize what we covered in this video. Accuracy may be reported as % recovery. Error is reported as absolute or relative, that is usually % error. Precision is a measure of repeatability. In the next video, we'll talk about how we actually quantify that. Systematic, that is determinate or type B errors, will bias the results and affect accuracy, and they can be eliminated. Random, that is indeterminate or type A errors, scatter the results. They affect precision, and they can be minimized by averaging, but never eliminated. So you've completed part 2 of this 4-part video series, and part 2 has dealt with accuracy, precision, error, and difference. Links to the other videos are on www.chemrad.com. You'll find part 1, Sig Figs and measurement uncertainty, part 3, standard uncertainty and instrument tolerances, and part 4, combined uncertainty, also called propagation of error, along with other video clips posted at that website, and like this gentleman, you can hurry right over there to access them. In any case, Thanks for watching.